file I/O and as well as string representations. So today, let's quickly share the screen. Bildschirmfreigabe, da ist Bildschirmfreigabe, Bildschirm Nummer 3. So what we can do today quickly before we start with a new thing, which will also be very interesting, let's quickly take a small look on what sorts of other issues we can encounter when we don't keep in mind the proper memory management. So one sort of issue I have already mentioned the last time, that if we allocate memory and allocate more and never release any or free it, then at some point we will just run out of available memory, so this is obvious. But there is another limitation which one should keep in mind, namely a limitation of the stack size. So as I said already the last time, on Windows it's limited to about 1 megabyte, and we can run a test where we have a function which we call stack overflow, which will then just call itself. So each time it does this, it will allocate some stack space and make a call. The next instance of the function will allocate some more stack space, and so on and so on and so on. And at some point, the amount of memory which was, or rather, most importantly, the amount of reserved address space that for the stack was envisioned will be just exceeded, and the application will crash. So we can run this quickly, and then, so as you also see here, the function is counting. So once we arrive in the crash, we might be able to see how many iterations, how often the function managed to call itself before the stack space was exceeded. Well, that was. It felt like it's quick. Let's see if we can read the value. Yeah, so it was 614 times. How often this, in fact, will be possible will, of course, depend on the amount of memory that your function or your whole function called tree uses. So in this case, we were allocating 1 kilobyte of memory for each function call. You can also look at the stack trace that we just see the function calling itself ad infinitum. And at some point we have the call from our main function. So of course, if we reduce this to 100, then we should be able to call ourselves about 6,000 times, more or less, which also is more or less instantaneous since computers are very quick. Okay, so effectively we were only capable of calling ourselves 2,500 times. But this is just a general guideline. So if you are writing functions and want to include any sort of recursion, I would say, if you assume that your function is not trivial and is not wasteful with memory, that you can call itself about 100 times before you will have a problem. And of course, another practical consideration is that how much stack space is left will depend on which function calls you. So if there is some other function which allocates a huge amount of stack space in one go, then of course this behavior will change. And since we were here now taking a look on exceptions, the next subject for the lecture will be actually exception handling. So as we have seen, it is easy to cause some sort of bug, and some bugs, of course, are not directly caught by the CPU, like a memory leak that just at some point will result in the program not being able to allocate any more memory, or other logical bugs which just make your program misbehave. This is, of course, up to the programmer to find and fix. But very simple issues can be caught by the CPU, like, for example, trying to access a null pointer, trying to access a memory address which is not valid, trying to divide by 0, for example, and alike. So let's create a new project in which we will intentionally cause a few exceptions. Why is it so slow? Okay, I have maybe not enough memory for the VM. Let's close one of the other Visual Studios. That should speed up things. Yeah. on this small tool here, the bar indicates the amount of memory used, so this is quite helpful. It's still. Wait, let's just restart it completely. Okay, it already. I will call it exceptions too. I will just put it somewhere else and then overwrite the broken instance. Apparently, it was already halfway through creating a exceptions folder, but it somewhere then got stuck. Okay, so let's just start with the already mentioned divide by 0. So let's make a function int x is equals 1, epsilon is equals 0, and z is equals x divided by epsilon. And of course, if we just call the function, then the whole thing should crash. And the debugger will report a divide by 0 or by null exception. And it does, as you see here, integer division by 0. The interesting thing about divisions by 0 is that they are only always captured if you are dividing integer numbers. If you are working with floating point numbers, you can actually configure the behavior of the floating point unit, whether it will raise an exception on a divide by 0 or if it will just write a special value that indicates that the result is infinite. So floating point mathematics in this sense on x86 are a little bit more flexible. But of course, in all practical cases, one should avoid such bugs. And of course, another exception we can fabricate would be just to try to dereference a null pointer. So we make some pointer, int asterisk x is gleich null, and then let's try to assign some value to it. So this will also cause an exception. And it would also cause a similar exception if we would just use some random address which is not mapped into our program's address space. So in this case, as you see here, we get exception from right exit violation, x was null pointer. So that works quite nicely. And now in various scenarios, you might not want your application to just crash when an exception is encountered. And to work with this, we can use the try keyword, and then we need a second one called except. It's preceded with 2 underscores. It wants an argument here, which we'll provide in a second, and then inside our try except block, we can, let's say, we do a division by 0. And the way this works is that when at some point inside this try block an exception is thrown, then the flow control will be redirected to this except code block, and you can provide an argument so here a return argument which tells what exactly should be done. So let's create such a filter function first. Int filter int code und struct we should include something before that. Hash typo include except struct underscore ax. Okay, the IntelliSense doesn't work again. Let's just copy it. It should be found somewhere. Maybe it's in Windows H. Ah, shit! I have here a typo. That's why I didn't found it. Now it's complaining. x. Oh, it's right. It should find it at some point. Well, it's not complaining that it can't find it. So the way we use this is we provide the function here to our accept keyword as an argument, and then we can get the exception code, and we can get additional information. And then within this function we can decide what to do next. And for the very simplest case, what we want to do is just we will want to execute this code block. So exception execute handler. So the exception handler is the code block here, and we can put there something that we see that it's doing. So let's include stdroh. Here we can put f. Exception. And now we can run the code and maybe put a breakpoint here. So we arrive at our function call, then we can enter the function, go through the jump table. Let's just go through this part, this is quicker, less clicking, and then we do our exception, and you see we ended up here directly in our printf function. So we will, as the next thing, print to the console that we caught the exception. We can add some more printf statements to make it clear how the execution flow behaves in such a situation. Then we start here. There might be an exception, or there might not be. Let's see. Then let's and then we can add some final comment. And what we also can do is we can add some printf to our filter. So here, okay. And if we are interested in what other values can be returned, we can quickly take a look on it. There are in fact 3 values which are available. So you have execute handler, which, as already described, is executing the code block. The accept block is preceding. Then we have continue search, which would mean that the exception will be then passed over to the next higher exception handler. And you have this continue execution option, which would tell the CPU to resume the execution at the last instruction which caused the exception, which, unless you do something, that would again cause the same exception again and again and again. So the idea with this continue execute is rather that if you would have some code where you know that if an exception starts happens at some point, what you need to change to avoid it happening. So it's a rather esoteric use case, but perhaps we could construct a actually working use case for demonstrative purposes. But first, let's run here our filter. Do we have breakpoints? We have breakpoints. We don't want breakpoints. So, and as we see, we started the first line, then we are in the try block, and then when we do the divide by 0, we end up in the filter, and then we have here exception and finish. So what we can now do is we can here use the code, the exception code variable to determine what happens. So if code is equals accept access violation, that will be the divide by null. Why is it not finding it? I think we need to include Windows H for that to be defined. Windows H. Yes. So this will be one case. So we can print f. Maybe we say in filter and don't say anything else. Just in filter. Here we say just say the string. And let's say return. So if we get an access violation, then we want to execute the handler. And the other scenario, or in else case, so what did we do? We divide by 0, so we actually need a different one. Let's put the reference null pointer here instead. Okay, and then we add okay. So now the behavior should be that if we have a dereference null pointer, then we will print this line and execute the exception handler. But if we instead trigger the divide by 0, we will end up here in the that's not right. I wanted to continue search here. Suck. But if we cause the divide by 0, then we will return continue search, and then the debugger of the program will throw us the exception and complain that something went wrong. So here again, why is that break? Okay, we need to turn this off. So the debugger, since it's a debugger, it can be set up such that it will always catch exceptions, even if there is an exception handler for them that can be configured for every exception. So now that I remove the checkbox, you see that we are here causing our access violation, and then continue with execution of the crash handler or the exception handler. And then if we do the other exception, we actually should get a proper crash, which we do. As you see here, it's an unconditional crash. We cannot continue from that in any way. It's just crashed and it's dead. So this is the general way how exception handling in C works. You can catch them with except. You can inspect what actually happened using some functions provided by the C framework. This works definitely on Windows. I have no idea if you have this get exception function that's called the same way on Linux or any other platform. But that's just something to check into in the documentation. The mechanics that you have a try and accept block will be the same. And there is one more thing which you can do with this try block. You can specify an additional. You can specify instead of accept also another keyword. So let's do that here. We make another try block in our first block, and then we make here a finally. This one doesn't take any arguments. Oops. Oops, small s, comma. We can use the function abnormal termination, which will tell us whether it was a crash or whether we just run past the function and finished the block in a graceful way. And another is normal. And what we also can do, so since we said we don't want to arrive here, we might arrive here, and here we write leave. The leave keyword will terminate your try block, and then you will automatically have your finally block executed, no matter where you are in the code. At any position, you can just write leave, and then you will skip to the finally. It does not work with accept, and I don't think you can cascade both of them at the same time. So in C++, you can have multiple exception handlers, but in C, you unfortunately cannot do that. You need to specify explicitly two try blocks with different termination statements. So let's run it. So we still have our divide by 0. Okay, now that one will crash. We want our exception handler, so we go to the null pointer exception. And as you can see here, so we start, we are in the try here, then we have our exception, then so in the filter of the access violation, then we have here the abnormal termination, so the block is already finished, and then we get the exception. So the order is we start here, we cause the exception, we jump to the inside of filter, then we execute this, and then we execute that. And we never arrive in those two lines since the exception could not be continued. And now if we would want to try this continue search, let me think if we can easily do it. The problem is that it really just resumes at the exact instruction where the problem happened. So if we would make like another thing like this and then just try to change the value of epsilon to 1, it probably will not be propagated to the actual instruction, because where we then load to register is already one opcode above. So this would not work as expected. I don't think it's really that easy to make such a thing where we could actually continue. So I think we might not do that. But we can try. Just try to take a look how this would look in machine code, and then we can decide whether it would be doable or not. Okay, so as we see here, yeah, we load the two variables, and then that might work because we take here directly the value from epsilon. So let's try that. So here we don't use the filter. We just tell it to we need some filter. Let's make a new function, filter test, to which we will pass the address of epsilon. Int filter test int stern epsilon. If stern per epsilon is gleich 0, then I did not enable that. That's a pity. This is such a nice feature. The one good reason to update to Windows 10 multiple clipboard. Right, and we will need to change this to 1. Is equal to 1. And else execute exception handler. Sure, we don't need to write else since we have a return here, so let's just write it this way. So the idea is the filter will check whether our epsilon is zero, then we know what happened. We could also check the code, but I'm too lazy to write that down right now. Then we will change the value, then we will return, and then the opcode here, which reads from the memory position of epsilon directly, should read a non-zero value, and then the division should work out. So let's try that. Okay, so let's go step by step. Oh no, it will not work out. I looked one line at the wrong position. That's not good. That will not work out. It is too long. Let's just put a breakpoint here until we... No, again. Okay, so we arrive here. Then we arrive there. Then we change it to 1. Then we say continue execution. We exit this function. Then we are here. This is part of the framework. Now it wants us to that some file which we probably don't. I think the C runtime is somewhere public, but I don't know which path that might actually lie at, so will go with the disassembly. So in the past, many of those things were completely proprietary, but I think recently Microsoft has made some of the C runtime stuff public. So that's that. Stepping through the exception handler might take a bit. Okay, we run again into the bug. Let's put a breakpoint instead of trying to stepping through everything. Let's just put again a breakpoint here where we have it, but then we will put a breakpoint to the actual opcode which causes the exception. Okay, so we are here. We want to do the disassembly. We don't need this. This one will cause the exception. So play. Now we make play. Then we are here. Then we make play again, and it didn't work. Okay, that did not work. I guess I said the problem is that it will try to do the operation from take the value from the register, which then again will not be correct. So let's just ignore that example. In principle, there are use cases where one can use this, but it's not easy to come up on the fly with a working one. What we could do, of course, would be to write some assembly code and then write an int3 or something that causes a breakpoint directly in there. What we could do is maybe we could try this. This should cause an exception as well. This one was not caught. Yeah, that much to this. Okay, so we have leave, we have that. Yeah, so I said I cannot show you an example for this continue search, but execute exception handler and continue search you have seen. Do you have any questions at this point about exception handling? No questions? Okay. Can you hear me?
Yes, we can hear you.
Okay. Good. So I will save this, and now let's take a look to one more interesting case. So let's create a new project. Let's create a new file. Oops. Okay. So, as you may remember from the last lectures, we spent a lot of time looking into function calls and how they work. And I was thinking that an interesting thing to show you before we proceed to the C++ part of the lecture will be how you can manipulate the execution of functions to just simply change the way a program behaves. So let's include Windows again. Oops. And just use some standard message box call. This function will just be an example. What's first? First is the text, so and some title. Then we can say okay. So as said, we just have a extremely simple now case where we are calling a function which is provided by as a part of the Windows API. As soon as it loads all the symbols, it will just pop up a message box saying test, this is a test. And what we will then attempt is we will try to intercept this function call using our own code, such that we can, for example, either completely suppress the message box or change what the message box is showing. It just needs here a few symbols to load before the debugger will feel ready. The annoying thing is that after every Windows update, if the file was changed, then you need to re-download the debug symbols for the new updated file. So this is a bit annoying, but once it's done that, up to the next Windows update, you will be left in peace. So here now it just starts outright, and just one more change. Let's go with the V version since it's more modern. So the APIs which end with a V on Windows take wildcard, wide-char arguments, such that you can use Unicode, while the A variants just take normal ASCII strings. So let's first see how this thing works from the beginning. So we want to have some pointer that will be pointing to our function which we want to hook. So let's call it this, and well, there are two ways we can load. We can go with the library v, which convert into the so if we are writing a normal program for Windows, then it will automatically include for us a huge amount of different libs. You can see them here. Input, okay, just says additional dependencies. It should, okay, it doesn't show the list. Sometimes, depending on the configuration, it shows actually the list of libs that it includes, but it includes often the user32 lib. It shows all platform. Let's switch that to the one we have. Usually that was, it's still not showing it. No, washed. But through including the user32 library, what it gives you is the ability to just call message box away directly without needing to import it. But if you would not have a lib that is associated with the DLL available, what you could do is you can use load library to load the DLL explicitly, and then you can use get prods address to get any export from the DLL that you might want. So in this case, again, the message box v, and we will just put a small breakpoint here, and then we will want to take a look where this address will take us. So we can just paste it here, and as you see, our system message box v variable contains the address where the actual message box lives in the user32 DLL. So if we check this, it shows here the symbol, so the DLL and then the symbol name. And in comparison, this message box we call here will take a slight detour first. So when we step in there, sorry, it was the wrong key. Again, if this window has the focus, then the stepping is only a one-line granularity. I should have not clicked there. So here, let's click. Actually, it even took us directly where we want to be. That's nice. In some cases, the invocation may take us through a jump list, but in this case, it didn't. So what we get here is really the memory address of the function that is being executed, and now we want to implement our own implementation of message box, which will, let's say, for beginners, just not do anything. So we take the same prototype, we call it my message box v. We make it return. Let's make it return a value int, right, and save the value here. so that we can show the returning. This we don't need, this we might need. Just make it slightly nicer. Okay, so what we will be now doing is simply we'll be trying to overwrite the memory at the location of MessageBox with a jump instruction to our own MessageBox function. So the first thing we will need to do will be to make this writable, because if it's not, if we would try to write to it without doing anything, we could actually try this as a demonstration. I will just first create a small helper function. Another function, helper union char Stern pb or Stern pw und Stern pd and oint64 pq. That should be worth not dot. Okay. So we can assign code pbyte to be equals to our address. We need a small casting operation here. And now let's just try to write a no x, what was it, cc I think. Let's just write a int free. Let's just interrupt free. It's a opcode just to cause a debugger exception. And now, but now when we try to write it, what we will get will be actually a crash, a memory access violation here, because we are not normally allowed to overwrite executable memory. So as you see here, exception, write access violation. So before we can start modifying our function, we need to remove the protection. Which we can do with the virtual protect function. We specify the address which we want to unprotect, then we specify the size. Let's say 32 bytes should be enough. And then we specify which new protection for the memory area we want. We want page execute read write, which is the one which normally you should never use, because it's it can be exploited in security exploits. So if you have a memory which is writable and executable, if due to some memory access issue someone tricks your program to overwrite that memory with malicious code, then the code will also be then able to be executed. So unless you are intentionally trying to do something more esoteric, you should not ever define memory as executable and writable at the same time. But for our particular use case, this is necessary. But since we want to maintain good practices, as soon as we are done modifying the code, we can use virtual protect again. Can copy most of that. We can copy the whole thing. And the way the function works is that whatever the previous protection value for this memory region was, it will be written. It will have been written to this alt protect variable. So we can now use it here to restore whatever original presets this memory area had. So the code now will unprotect the memory, modify it with a debug break, and then restore the protection. And here we will try to call the code which we have just hacked. So let's run it. And now we will step through it. And as you see, we arrived here in this address, and here is a CC which we have written there. The other CCs were there already before, but this one is ours. And when we try to execute it, we will get our debug exception. Or our debug break. The way usually you call it a debug break, but it's implemented just as an exception within the CPU, so both terminologies are valid. So what we will now want to do is we would like for fun to write some assembler code by hand. So to do this, I already showed you a website which helps with that. Let's quickly find it again. No, that's not the right one. That's the right one. and it's quite nice because it has both functionality. You can assemble and disassemble Intel and ARM64 code. So what we want to do here, so we can first of all comment out our debug break. And now first let's write some comments which will depict what we want to do. So one thing we would want to do is we want to move rux. We want to move something into the rux register. And we need a variable for that. Void my message box here. Let's just get the address of our own message box implementation. So we want to move the address into the rux register, and the next thing we want to do is just jump to the rux register. So it's as simple as it gets. So we can just copy the code, mostly at least, and paste it to our assembler. Of course we cannot use the label, we need to let's just use a placeholder such that we see what code it generates, and we can easily spot within the opcode which bytes we need to replace. Why is it complaining? Okay. Right here, so let's quickly grab the code with the explanations. And the strange thing is this is not a perfectly working website, because if you use just if you write move apps, then it doesn't like to compile it. You need to write move, but when it decompiles, then again use the move apps opcode. So it's, well, it works, but it's not perfect. So let's write this somewhere here as a comment. Okay, so we see that this part is basically just our address, so the interesting part are just those two characters. So we can use our helper union, where we go to the word. And the way this helper union works is, as you may remember from the lecture about structs and unions, all those variables share this exact same memory area. So whether I access p byte, p word, p word, or the p word, it will be the exact same value. But since the types are defined differently, what the compiler then does with it will be different. We can first of all dereference our pointer using asterisk, such that we can assign it a value. If it's a word, we can assign 2 bytes. And then we have the plus plus, which is after the variable, not before, so that once we are done with the operation, it will advance the pointer to the next address after this size of machine type. So it will always, so in the case where we use the b, it will only advance by 1 byte. If we use the word, then it will advance by 2 bytes, and the next thing which we will need will be the word, since when the full address. It should be below it. Okay, cool. Then it will advance by 8 bytes. So what we want here, we already said, we want this to be that, and here we want to write our 2 bytes. And as you might remember, because of the endianness, we first need to write the last byte, p8, and then we can write the first byte. So this is a bit counterintuitive, but that's how it works. In memory, it will swap the positions of those two, so we will get 48b8 and then our address. So we get our move rux, and then what we want is our jump instruction, which, as we see, is a 2. Why is it complaining? Cool. Okay, yes, it's complaining because the type is void asterisk, and we want to make a small typecast here. So the next one which we are assigning will be again a word, null x, a null, ff, large e looks better. So we are just jumping at our rux address, and at this point we already have implemented a very simple and trivial with complaining still. Ah, shit. I forgot the asterisk there. Okay, now it's fine. So this is like the simplest way you can detour a function. You're just taking its address and overwriting the beginning with a jump to what you want to do. And this will work and not crash. The main drawback of doing this at this point is that we can no longer call MessageBox at all because we have just destroyed it. There are two ways how this can be later mitigated, which we will take a look at in a second. But let's first run it and see how it behaves. So again, we are done with our messing with the code. Here we have our call instruction to our message box. So let's call it. And here, as you see, we have our what can I hide? Source code bytes. Let's not hide anything. You just move it. So the source code bytes are boring. Let's hide them. Yeah. So as you see here, we have our rex move rex instruction, and then we have our jump instruction, and the rest is of course whatever was there before. And when we make the jump, then we arrive at the jump table of our own program, and then we arrive in our function, through which we can step through everything, step over that, and then at some point return execution. And once we put a breakpoint here, we see that we have even returned the right value. Let me quickly change a few presets here such that we will get cleaner code. So general, what was it? Yeah, it was one of the things. Nope. And the other one, runtime, basic runtime checks, and none. And we don't want security checks either. Okay, this should give us a much cleaner code. I forgot to disable one thing. Let's quickly do that. That was somewhere with the linker, if I remember correctly. All options. Was it here? Or maybe it was at the C part. No, this one. We don't want this one. No incremental linkage. This creates these jump tables, which are annoying and unnecessary. Because now if we make the call, we get here, and then when we jump directly to our function, which doesn't do much, just saves the four parameters and then returns. Okay, so now let's assume that we would want to call MessageBox from within our function, or we want to make the program able to call MessageBox at some later point and not detour it each time. There are two strategies how this can be achieved. One is a very brute force and straightforward approach. Just once we arrive here, we can overwrite the code which we have overwritten before with a backup copy that we would have to make before we change it, and then this would work. And first of all, we would be able to call a MessageBox to, for example, show a MessageBox or for whatever other reason. And secondly, the program in its later execution would be able to call MessageBox without being detoured to our detour function anymore, which in some use cases is fine, in other use cases is not what we want. So the most advanced use case we would have would be when we want to kind of filter all the MessageBox calls, which may they be, however many they may be, and then make each time some decision, or maybe log into a text file what messages the MessageBox has thrown, or anything of this sort. So what we want is we want to find a way to make MessageBox work while it is still hooked. So it might appear at a first glance that this is not necessarily fully straightforward, since when we overwrite it, how can it keep working? But given how the execution in fact works, this is not that difficult. So let's start by making a breakpoint here. So what we will be doing now will be creating a so-called trampoline function. So a trampoline function is a function which allows you to execute some function which you have a portion of it overwritten, and it's designed in a way that the all the operations which are supposed to be executed before the unaltered code starts will be executed by the trampoline instead of the code which we have before changed. And of course, then the last instruction from our trampoline will be to jump to the untouched portion of our target function. So first, we need again the address, and we want to take a look. So we want to take a look how our function looks. So here, let's take maybe until here. How many bytes are these? Should be enough. I mean, we can take a few less or a few more. Let's just take this many for now. We don't need the addresses. Let's just take these, write them down for later reference. Okay. Show addresses and stop. So we know what the function did originally. Of course, this is now a very manual approach. Ideally, when you are hooking functions in programs in production, you would not want to have to write a detour to write a trampoline by hand, because you don't have a guarantee that the function which you will be hooking has not changed. So if you have different versions of some software, which for example Windows, which then may at some point change the implementation of MessageBox-V, then you might run into a situation where your handmade trampoline would not longer do the correct thing, and then just end up in a big crash. So in production, what you would want to do is you would want to use a library which intelligently analyzes the beginning of the function and then dynamically generates a trampoline for you. So doing it manually we'll do now once for pedagogical reasons, but this is not something that one would use in production whenever available. So let's start. So here we can first of all count how many bytes we need. So we have 2 bytes here and 8 bytes, that's 10. So we need 12 bytes in total, which will be overwritten. So 12 bytes, 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. So we need until here. We need to put this much code into our trampoline function. So let's do that. One thing which we will need will be some memory into which we will write our trampoline. So let's maybe here allocate some memory. And another thing we would probably want is we would want the memory to be as close to the original function as possible. So let's go with and create a for loop. So we take the original address, and this should be capital. At the starting point to start off, we don't have a break condition, but we want to go in increments of 4 kilobytes, so that's about page size. And now we need another variable for that. Since we want to call it from here, we will define it at the top. And also, since we want to use it, we will not define it as a void, but we'll actually give it a type. So we will create a type def int asterisk pointer to message box. So this is our type, and now we can use this type. Tram message box v. We start with null since we don't have a value yet. And now here inside the code we can assign this and use virtual alloc to allocate some memory. We can specify which address you would want it to be allocated at. We start with @, then the size. Let's again say we need 32 bytes, and then we want complete, and we want, of course, page execute read write. That was supposed to be an add. Page execute read write, such that we can work with it. And if this is not null, so if the allocation fails because, for example, it was already allocated, and it will return null, but if it successfully finishes the operation, it will return us pretty much the same address we requested. So here, if that happens, we can break. Okay. So we can use our helper structure again, and assign it this. Okay, so first we want the first instruction. So let's double word asterisk plus null x, and then we just need to copy it from the beginning. It was 38 EC 38 48. So this is our soft SP. Then we want the XOR. RD. So unfortunately we don't have a 3-character large type. So let's go with using a first a double word. No, sorry, first a word and then a byte. So the word we want to start here will be 3, 4, 5. Then the byte code p byte plus is equals null xdb. So this is our XOR operation. Well, both of those lines, and then the next thing will be already our comparison operation here. So 1, 2, 3, 4, 5, 6, 7 bytes we need for that. And one thing that can be noticed here is that we are here using some offset of something, so probably when we just copy it, it will not work correctly. But for starters, we could just try copying it and then debug what went wrong. So let's go here, code, how much they count? 7, right? 1, 2, 3, 4, 5, 6, 7. So let's go with a double word. Okay, so it starts from here, 7, 2, 1D, 3, 9, 4, 4. Then we have a word. X will be those two, 0, 3, 9, 7, and then we have a byte. There is equals null. Let's write like this. Okay, let's just tab everything by one. And now, so this part will not be right. We will need to fix it later. But first, let's finish the trampoline. So now, the thing we want to do is we want to jump to our remanent, to the rest of our function, however you would call this. So we have here, we will just use the move ups as well, but what we want to calculate will be first a trampoline target. So let's calculate this quickly here. 64 trampoline 64 trump target is equals alright, yo, that will be just the address of the message box, the original one. Minus a plus. How many did we say? 14 plus 14. Okay, so this is our trampoline target, which we can then just write here, and we have our jump praxis instruction, which we are happy with. So let's try that. We don't need this breakpoint, we need the other one. Yes. Okay. We forgot something. We have not invoked our trampoline. That we should do here. We can call it just normally. Let's say we use the same and also the same text, but we change the caption to our own. And then we leave the last argument again the original one. So we only change the title of the message box and to return the original value as well. So let's actually, we can put a breakpoint here, and then we can, we don't need to step through everything, we can just jump to our detour function. Since we already stepped through this jumping portion before, we don't need to redo it. And now here we will now invoke our trampoline. So we go to call, and you see we have our soup, we have our XOR, then we have our compare instruction, and we have our jump. And if we make this, well, if we step through this, we already here at this compare line got a memory access violation. And the reason is because the value here, which were actually this number here, is invalid. And it is invalid because the way the instruction is specified, or was specified, is a position dependent. So when the code is invoked from a different offset, the resulting number will be a different one. So if we decode this instruction, we get so if we decode this instruction, we get an actually much more helpful disassembly than what Visual Studio provided us, because actually this thing, as you see, it takes, so it compares the register R11 as a double word with memory at the location of the instruction pointer plus this number. And since the instruction pointer, when we are in our trampoline function, of course has a different value than what it would have when it would be within the original function. So then obviously the whole memory address gets messed up. So what we now need to do to make this detour work properly will be to calculate the displacement of the trampoline and then add this to the old values. So let's do that very quickly here. In 64 the is displacement equals so the trampoline displacement will be _10 because we want this individual steps. We need the trampoline of the message box, and then we subtract from it the actual address of the message box. So since we here are always incrementing the address we try to obtain, then we know that the trampoline will be a larger value than the original address. We could of course search here in both directions, in which case here we would need to also take into account whether it's positive or negative. Okay, so, and let's also change slightly the way we wrote this whole thing. We can again use our helper side here to get a better insight into the binary representation. So one thing that is already obvious from the amount of characters here, which is, what was it, 7, is that you cannot use a 64-bit offset here in this operation, which is, for example, one of the reasons why we wanted to find a detour, a memory location to create our trampoline, which is as close to the original as possible. Because if you would have a memory at the location which needs here more than 64-bit of address, more than 32-bit of offset for the addressing, then we could not in an easy way modify the existing instruction. We would need to write a couple instructions in its place, and that would complicate things a lot. But since we are close enough, then we will be able to use it mostly unchanged. So here for testing we'll just write something that we can easily spot, A, B, B, C, C, D, D, for example. Okay, that's already too much. It should not start with an A. We need to start with something smaller. Let's go with F 80. Oops. 80 B, B, C, C, D, D. That's fine. No. Okay, no. Okay, that worked out. That worked out. So we see here that the last 4 bytes of the opcode are the offset, and the first 3 bytes are the actual opcode portion of the opcode. So we will want to change the way we did it here. So we need to do this again. So we have here our opcode. Actually, I can copy this portion here. The next one was D2, D1. Yeah. And then we have our address, which was 00037972. Okay, and now if I'm not mistaken, we need to subtract the displacement from this, and now we should have the valid address as a result of the operation. I think that's correct. Let's try it out. And one more thing, we could or should after we are done creating our trampoline, probably protect the memory such that we don't create for anyone an opportunity to exploit our code. So we go with mytram page, but we don't have like an old value to use, so we just go with page execute read, and as long as it's not writable, it's safe. And wait, was 32 enough? Should we allocated 32? We could count all the bytes, but I think that will be fine. It should be fine because we go by displacement 14, and we know that this code only consumes 12 bytes, so we are far below 32, so this is fine. So let's run it again. One more. Okay, now we will step here. So we are jumping to our trampoline, and it executed the CMP operation successfully. We also see that now that it points to different memory, Visual Studio shows us the symbol of that location as well as the address here. We can compare the address whether we came up with the same one, and as we see, it is the exact same address, which now effectively will be here compared against. So we can continue with our jump to the original function, and then we are here already within the original message box function. The code below was not altered, so we can just run, and we have our hacked message box window. As you see, the title was changed, the rest of the function was not. The behavior is the same, and then we have, of course, our return, which just says that we press the OK button. Let me do only one more improvement. Let's leave this as is and write this down here. Yep. Okay, any questions? No questions? Okay. So, then the next thing that would be good to try So first of all, maybe a question from me. Is this interesting to you? Do you want to learn more about function hooking? Well, no one says anything.
Sorry. I would have a question.
Yes?
With where you copy the opcodes, or rather the assembly,
Mm-hmm.
into the memory location where increment the pointer of this helping.
Mm-hmm.
How does this work so that can you reuse the union to fill the memory with this increment? I don't quite see.
Okay, we can step through it and see step by step how this operates. So we start by assigning the memory location which we have obtained from our virtual alloc function to our variable here. So let's go here to watch and add the item, and then as you see here, it tells us what is it, which address this is pointing at, and if we add other of those, like word or double word or the word, you see that they are all pointing at the exact same memory address. That's the behavior of a union. And then if we arrive at this line, what happens is that we can choose one of these types. So if we choose, for example, the type D, so it's a double word, so it's a 32-bit number, then the compiler will take this memory location and treat it as a pointer to a double word, meaning that if we dereference it, we can just assign to it a 32-bit number, and also meaning that if we increment this by 1, the value as such will change by 4. So we can here make one step now, and as you see, the number here, a 4 was added. So initially we had just 4 zeros, but now it increased the whole thing by 4. And if we go to the memory location at this point, memory 1, we actually had that open. Let's go to the original address and make it bigger. Yeah, so you see that on the 4 bytes have been overwritten, and then now what we have here is a word, so it's only 2 bytes. So when this will be executed, it will only copy those. No, that's not the right ones. The one somewhere there was a 0. 1. That's already this one. It will only replace those 2 here. Let's do that. Click. You see, it replaced those 2, and now it changed the value from 4 to 6 because we increased a word pointer by 1 element, so it increased the number, the actual mathematical number, by 2. And then if we do the same for byte, it will only increment it by 1 and only overwrite 1 byte. Let's do this again. It only overwrote 1 byte, and now it increased it from 6 to 7. So using a union here like this makes the compiler take care of advancing the pointer to the next free position, and allows you to use any size of machine types that you might want to use. As said, one limitation of this strategy is that you cannot assign 3 characters at once, so you need to break it up into 2 assignments. Is it clear now, or do you have more questions?
Yeah, now I understand it.
Okay.
So essentially the whole point you increment, but using different incrementations depending on the type.
Exactly.
Thanks.
Mm-hmm.
Now I get it.
Any more questions? Okay. So if there are no more questions, then what we could do now is we could try to do something useful with our newly learned powers. of detouring API functions. So let's create some target process, new project. It will be again a console application. Hook target, create, and inside it we will again include Windows 8, and then we will say, let's see what we will do. We can make an if null L question mark comma L title comma mb yes no mb icon question, and if this is ID yes, then we will fail. And return a error code. Okay, for printf we need to include stdio. Okay, so if the user selected that no, he does not want to crash, then we can show another message box. Null comma L let's be still annoying about that, so title mb okay, mb icon exclamation mark, and then printf okay, and return 0. So it still complained that it doesn't work, but at least it successfully finished. So that's like our test program which we will be messing with. Let's quickly disable all the things which we usually want to disable, this and that and that and one more thing, this one. Okay, so now let's also create a new project which we will use to start the target process and manipulate it. New project, let's call it DL injector, or maybe large else, because the small else in, or inject DLL. That looks nice from the graphical layout. So again, we want here to include Windows H and stdio, because we probably want to have printf stdio. Okay, one nice thing that Visual Studio allows you to do is to define the relationships between projects. So you can go on properties, then go on project dependencies and select the project you want to say it's dependent on something. So our DL injector, for example, will be dependent on hook target. So this means that when you now want to start a hook target, it will compile both. Sorry, I didn't set it. We also need to set it, of course, as startup project. Now it will work. So now it will compile both of the projects and only start once both have finished compiling. So as you see here, it compiled hook target, and then of course we are now here in the main, which doesn't do anything yet. But this is already quite useful if you have a bigger project with a lot of DLLs and other dependencies, that you can tell Visual Studio that it needs to build those elements before it will build your project and run it. So this is a good thing to know. Alright, so one thing we will of course need is we will need to create the process, create a process that will be running our hook target. So let's start with finding out where so the idea how this will work is that we just will take the current directory in which the current executable of inject.dll lies, and then to that we will then add the name of our target process, which it will then start. So path max path get the function get module module file name v when provided with a null instead of an actual module will return us the address the path to the current executable, and we need only to provide it with a buffer, and we need of course also to say how large the buffer is, such that if the buffer would be too small it will not overwrite it. And ideally we should now check the return value, and if for example the buffer was not large enough, then fail or try with a larger buffer. But since this is just a demo, we will not do that. And one thing we want to do is we want to remove the file name of the current process from the path. So we will use the vcs rchr function, which searches a wide string for a character, and it does this in reverse. So it searches from the back, so we can specify // and ideally now we should check whether the result is actually not null, so because if it fails to find the character it is supposed to search for, then what it will do is it will just return null. But since we assume this will work, we just advance it by 1, dereference the whole thing, and assign it 0. So this is very unsafe code. You should not do that in production, but for a demo this is good enough. And now we create a new buffer. I mean, at some point we could also just reuse this, but we will want to have two paths, so we need actually to copy it. So we of course need to rename it. Let's call it exe path wcl target source. You could also try to be smart about it and get the offset and then use a vcs copy n that only copies a certain amount. Or that might actually not compile and complain that it's not safe. Which one want this one? I think it will complain. We have not turned it. We have not told it not to complain. So we need at least to provide here the additional argument and use the s variant. Okay. And what we can then use is vcs cut s, which appends something to a string. If I remember the syntax, it's just the same, plus whatever we want it to append. And how did we call it? Hook target. Exe. The backslash we have kept. So since we advanced by 1, the pointer was pointing to the character after the backslash, so that backslash is kept. So we will have now the right path here, and now we want to start the process. So startup information v se. We initialize the structure with 0. Then we want to add with a process information. Does not use any string, so there is no a or v variant. It's just what it is. And then we can use the create process v. Oops, I forgot the semicolon here. We can use the create process v to create a process. So first argument is just the exe path, and then there is a huge amount of additional arguments. You can specify a command line optionally. We don't want to do that. Oops. You can specify security attributes. We also don't need that. Then you can specify another set of security attributes for the initial thread, or thread, not thread. Then we can specify whether the program should be able to inherit. Now whether the handle that we get returned will be inherited handles. We just say false. And now we can specify the creation flag. These ones are interesting because they allow us to create a process but not start executing it. So we use the flag create suspended to just create a process which doesn't do anything and waits to be resumed. And then we don't need the custom environment. We don't need, what's the next one? So if we provide null for the current directory, it will just take the current directory which we are in right now. We could, in theory, provide a alternative current directory. And then we provide our startup information and our process information pointers. So the startup information can have a few more parameters configured, as you see here. Desktop title for the window position, size of the initial window, that I don't know. They don't know either. Flags, that will be, for example, how the window should be shown, or that's actually probably the second one. There is a manual for that. We can actually quickly take a look how this is specified. There are so many things to remember that I just usually don't remember them. Instead, just always review the documentation. And here, for example, on the Microsoft website, they document the whole structure, all of the arguments, and then they will tell us what flags are allowed. So we have here a huge amount of different additional flags which can be used. Show window specifies whether the window will be visible or invisible. The reserved ones are just, well, reserved. And that's it. Don't care for the rest. And the process infrastructure, this one. So this one specifies information how the process should be created in addition to those parameters which are provided already here. Since they didn't want to make you type like a good 2,000 parameters into as arguments, they just provided this structure for the additional less commonly used ones. But the process information is different. It is not initialized with anything, but it will receive 4 values from the create call, namely a handle to the process that was created, a handle to the first thread in the process which was created, and the process and thread IDs. These informations are to some extent redundant, because if you have the thread ID, you can open a handle on a process, and if you have a handle to a process, you can find out its ID, but it's convenient to have both provided as is. And again, we probably should check whether there is some error or not, but since we don't care, we won't. And since it was created, so here we will want to do something later. But the last thing we need to do is, of course, we need to resume the thread. So we use the handle which we were given. Actually, the handle to the thing is quite useful for those things. And in theory, we need to close a handle for this and that. But in practice, since we are terminating anyways, we don't care. So when the program is terminated on Windows, will, or on Linux, then the Linux kernel, close all handles which are only held open by this program, and release all memory which is only referred by this program. So if you write something extremely short which is not supposed to run for a long time, you don't necessarily need to follow best practices with regard to resource usage, because as soon as the program is terminated, the resources will be freed anyways. But of course, the more pedagogically valuable approach would be to always write perfect code and don't take any shortcuts, because at some point you might want to reuse the code in a bigger project, one which is not supposed to terminate after a few seconds. And then if you integrate some resource leak, then this will be a pain to debug later. But we can now start this, and the result should simply be that we will get our that's missing. That we will get our target program started. One I think I would want to add here from the online market is a tool. This one, a tool which will okay, I need to restart Visual Studio for that. So the way this works normally is that Visual Studio, if a process that you are debugging starts a new child process, then the new child process will not be debugged. But in our use case, we actually want this to be the case. So with this child process debug extension, which can be found in the Visual Studio store, this can be changed such that whenever a new process is created, the Visual Studio debugger will automatically attach to the newly created child process. The installation will take a second. Or maybe two. Why is that so slow? It's not doing so. At least this tool doesn't show either CPU nor memory usage. Is the hard disk on the limit? No, it just... Nothing set the limit, it's just slow. Or actually maybe it's using one of the cores fully. Yeah, on average that might be it. If we take a look into the other tool. Here, thread, thread, tokens, threads, CPU. So the thread, this shows the CPU usage for every individual. So when here you see a 100%, it really is one full core, not like the whole CPU. So if we see here that we are close, though it's not refreshing, that's also strange. Is it done already? Oh, it finished. It finished, that's why it wasn't refreshing. So this is one of the limitations of you might run into if something is slow and you don't see why it's slow. It's always good to check whether it's probably something that is just one thread using one core and it cannot use more than one core at the same time. So then it will still need time, despite the fact that the computer would have plenty of spare computing resources to be used by other processes. Okay, Funkhook test. We can close this. Funkhook test. Yeah, debug. Now we have a new entry here, child process debug settings, and we can check the checkbox, save the save box, and then when we run it, we can put a breakpoint here, and we should arrive at it. So let's first go to our injector here before we resume the thread. So it created the process. If we now look into a task manager, we'll already see it being there here, hook target. This particular task manager shows suspended processes in gray, so you actually see that it's not doing anything. And now when we resume the only thread the process has, we should be... Yeah, we will get, do you want the program to fail? No. This program does not work, and my typos are terrible. And then we arrived in the breakpoint in the other process. My most favorite typos are when I mix the letters which I would write with the left hand with the letters that I would write with the right hand. That's somehow lack of multi-thread synchronization in my brain. Okay, but let's now continue with what we want to do actually. So here we will want to inject some code into the target process, and to do that there are quite a few different strategies. So since we have a handle on the process, we could just write into its memory some code, so do something in a way similar to what we did in here, like really manually everything. But there are much easier ways to get get code execution in another process. So we will, since we only have less than an hour left, use one of the simpler methods. We'll just create a DLL, which we'll then inject using a very nice trick at new project. Which one will be the right one? We just want a normal DLL. I think the first one is just the simplest one that is good enough. And we call it hook DLL. Create. Okay, yep, that was the right project. So we only have this DLL main, which is kind of the analogous thing to a main in a normal program. The important difference is this DLL main, in contrary to the normal to a normal program's main, is called multiple times. So, and in a normal program, when you start the main function is called once when the program is loaded, and that's it. In a DLL, this DLL main function gets called actually in 4 different conditions with this reason variable set to a value which denotes which event it was. It's get called once when the DLL is loaded by a process, so it's comparable at this point with the main. This is the process attach. But then each time a new thread is created within a process, you have this thread attach event. Then when a thread terminates, you have this thread detached event. And then when the DLL gets unloaded from the process or the process terminates, then when it just terminates with exit 0, then nothing happens. But when it terminates gracefully, it will usually first unload the DLL. So then you will get here a notification as well. And what you also can do is you can actively unload a DLL from a process at any given point in time if you want to do that for whatever reason. Okay, so we have here our DLL. Let's now go to our dependency settings. Project dependencies, DLL inject, and say that we are also dependent on the hook DLL because we want it to be rebuilt each time we do something. And then in process attach we'll get a make a break, and then later we will fill the DLL with some content, but for now we just add a break. Okay, so now we will inject the DLL into the other process. So to do that we will need first of all the path of the DLL, which is easy enough to obtain. We just use the same trick as the last time. We use the path we already had. Just here we insert what was it? Hook DLL.dll. Okay, and then we need some memory within the new process, which we will write to, which will write the path of the DLL to. So void asterisk address is equals virtual alloc nx extended, and then we can provide the process handle. We need the VM write permission on the handle, but normally when we create a process we have all the permissions there can be. We don't care for a particular address, so just null, but we need to have enough space, so we provide the size of our DLL path, and then we need to set a few flags, and we want page read write. It doesn't need to be executed because it will only be used as an argument storage. Now we write process memory. We provide again the handle, comma, address we already had, that's this one. Then we provide the buffer, that's our memory. Then we provide the size. Can go with copying the whole thing, even though we could also just go with VCSLN and then just only copy the amount of bytes needed. And what we also get is we can get the amount of bytes that have been actually written. So sometimes it may fail in a way that it writes some of what you wanted it to write, but then it doesn't manage to write the rest. So this might be useful, but since we have a small amount of data, this is not expected to happen. So we just provide null and don't care for the return value. And now what we need is the address of load library v, and we can obtain this the way similar we obtained here before our message box address. Sorry, you just need one asterisk here, but this will not be used for that can refer to. And here we want load library v, and this gives us this out. Okay, and what we will now do is we'll create a new thread within the process, which will execute before the actual thread which was actually created. Using the create remote thread function. So we again have to specify the process in which we want the thread to be created. Security attributes null, stack size Um, Actually, we don't need to provide this text, as we can also go with 0. It can just take the default. And then what we provide as next argument is the address within the other process, at which the thread should start execution. And the way the DLL loader in Windows works is that if you have a DLL loaded, then normally in all other processes it will be loaded to the exact same initial address. And the idea here is that when it's loaded this way, then then relative jumps or even absolute jumps within the DLL will work in one program and in the other program as well. So the memory, so both programs have their own virtual memory space, but whenever possible, Windows will try to use the same physical memory of a DLL and share it between multiple programs. This way, if 10 programs use the same DLL doesn't need to be loaded 10 times. However, since the memory is shared and you don't want a program messing with what it perceives its own memory, breaking some other program by overwriting its instance of the DLL, Windows implements here a copy on write semantics. So when you have the second instance of the DLL in another program loaded, it will use the same memory as another one. But if any of those then tries to write to the DLL's memory locate addresses, then what it will do is it will copy the whole DLL into another, or maybe just a page of it. I'm not sure about the granularity with which this mechanism works, but it will copy at least the page which you want to alter to a different physical location, allow you to alter this copy that is now yours, and within your own memory address space, this page which is now somewhere else will look like if it's still inside the original DLL. And as said, for this mechanism to work, it is necessary for the DLLs to be loaded to the same addresses as often as possible. So we can, with this cheap trick in our own process, determine at which address a DLL and thus subsequently a DLL's export function, well, any function export by the DLL, basically will be located. There are cases where this might not be the case. So if, for example, we would start up our program, then use virtual alloc to allocate a memory which we know will conflict with a DLL which is already loaded by the system, and then tell the system, hey, load me this DLL. Then the system will say, oh, I cannot reuse this memory area. So, and it cannot just remap a DLL as is, because the DLL may contain absolute jumps or other comparable not necessarily nice things. So usually you cannot expect machine code to be a position independent. So effectively what happens is when the DLL or any other or a binary of any sort is loaded by Windows, is the file format contains a list of all the locations within the code which contain position dependent offsets, and the main header of the binary also contains like a preferred address where the DLL or the binary would want to be loaded to for those values to be right outright. But often it's not, or well, there are multiple reasons why this might not work to give the DLL or binary the address it wants. First of all, as already said in the earlier example, some allocations within a program may have already used this memory, so when a DLL is loaded later on, this memory cannot be used. Or another reason is actually a security reason, namely that nowadays you don't want hackers to be able to guess the location of DLLs in memory if they come from outside the system. So each time you load a DLL for the first time on Windows, it will, when possible, try to find a random location in memory to which it will map the DLL, such that an external attacker will not know the right offset to address. But anyhow, to make the DLL or another binary file work at arbitrary load positions, the file format contains a whole list of this position dependent opcodes, and then when the code is loaded, the loader will just see, okay, I was supposed to load it there, but I loaded it somewhere else. So what's the difference? Okay, that's the difference. So now let me change all the opcodes by this difference. So basically, it will do automatically what we did here by hand. It will calculate the displacements and update. So effectively, if you would save a DLL from your computer's memory to disk and compare it with the DLL as it was, as it physically lives on your hard disk, then you would see that they will not be identical. There will be many small changes, except of course if the DLL was loaded to the address it wanted to be loaded and they did not have this address space randomization enabled. So this much to that. But anyhow, there are of course other ways how you can determine an address of a DLL. There are Windows system calls which you can use to enumerate all the DLLs loaded by a given program, and then if you have those, you can directly from those get the base address of the DLL from those information. So this could be used here as well, but since this complicates things and we want to be rather simple, we will just use this trick. So we just provide the load library v as the entry point for our new thread, and then what we can specify is we can specify one argument which will be passed to the function. And coincidentally, the load library v function only takes one argument. As you see here, it just takes the file name, and actually it takes a pointer to the file name since it's just a pointer to a C string. So here we just use our address as the argument, and effectively what we will do is we will execute load library v within the new process with the path that we have just specified, and this will load our DLL. So creation flags null since we want the thread to start outright, and thread ID we don't care for, and set and what we can do now here is we can wait for this execution to finish. So we don't want to resume the original initial thread of the process before we have finished executing our hook DLL. So here we make a use oops, wait for single object. We provided the handler and we can tell it how long to wait. If we say -1, it will wait forever, unless of course the event is signalized. And a thread gets signalized or signaled, I'm not sure about the right English, gets signaled when it finishes. And in this case it finishes when the load library function terminates, and the load library function terminates after the DLL main function has finished. So now if we run the code, the flow should be like this. Let's say we arrive here, then we will arrive here, then we will arrive here. This one we don't care for, and then we should arrive, well, first here, first there, and that's that. So let's run it and see if it works as expected. So we now will create our remote thread. Is it working? It's just hanging. What's broken here? The threads are suspended. This one should not be suspended. But maybe it is. It might be that it copies the state of the whole process. If the process was suspended, then it will suspend the thread as well. Or it's crashing. It's rather crashing. Or maybe I should not trust this this one. Let's turn this off and do it manually. Yeah. So again, before we inject the thread, we arrive here. at this point, this thing doesn't do anything. It just has one thread waiting to do something. So we can debug attach to process to attach to another process. Attach. Okay. You can also inspect whether the DLL path is correct. It looks like it is. We can check whether DLL actually exists where we want it to exist. Yeah, the DLL is also here. So this looks fine. They remain. Wait, this is complaining because it's not yet loaded. This is normal, so let's continue. And continue. Okay, it crashed. What did we screw up here? We have our address, write process memory. Page read write should be fine. Load library should also be right. Start address. Oh, our load library is wrong. Why is this wrong? Because this is wrong. My favorite typo again. Okay, now it should work. It would work if we do not have forget to enable child process debugging, so let's quickly attach manually. And we have a dead instance from before, so let's kill it quickly. Now it should work. Continue. It didn't crash, but it did not work correctly either. So let's first re-enable child process debugging, because maybe we just did not manage to get in at the right moment in time. Let's rebuild this just to be sure we have. Wait, that is still running. That's not good. Minute. Okay, now it's built. Let's try again. So we are here. It's not working. Right, this was loaded, this was loaded. So this should be working. We can try to use the other address. But I don't think this will make a change. Handle process memory. Let's see if that was working right. So we got an address and rewritten successfully. We can go there and put a breakpoint at this address. Nope. I wanted to change this back. Why is that not working? That was usually working. I forgot something. No, I don't think so. Yeah. But we don't have, didn't make us just a suspended thread. Those threads are at random locations. They should not. Why is that not working? That was usually working just fine. Create remove thread, process null. Start with our load library address. Address null and null. That should be fine. But also if the thread would crash, it should still signal the event. I mean, we can remove this temporarily and then just see what happens if we resume everything without waiting. Yeah, but then we just get into main and our DLL doesn't do anything. Was it loaded though? Modules. It was loaded, it just didn't do anything. Okay, let's put just a debug break here somewhere. Then we should definitely break if it's loaded as it should be. Nope. Okay, so if we yeah, but because now we didn't wait. I think it's created suspended. It should be created normally. A second resume should not be needed for that. But it did not resume the thread. Why wouldn't that resume the thread properly? Should be able to create the thread, and then we can try to specify explicitly that we want it to be suspended, and then flex create suspend. Maybe I need to specify a stack size. Okay, let's specify stack size. X1. And put a breakpoint here. Okay, so our entry address is 806A null. So let's see our threads. It did not create the thread. And the handle, it gave us a valid handle. It does not. Wait, was it a null or was it not a null? Oh no, it created it. Sorry, it created it. It's this one. So we have the thread, and now if we resume it, it's not resumed. Why is it not resumed? No, it was resumed and was terminated. So it did something. When we now go to modules, it didn't resume it. It's not my name. Yeah, if I resume it manually, why is the resume thread call not working? Let's try this. Let's just let it sleep for some time and not create suspended, just a normal one. It's not elegant, but it seems to be creating the thread, and it seems to only suspending it when we say it that it should be suspended. The remain, but it did not break in here again. It hasn't yet loaded the DLL, really? This is still suspended. Why is this one still suspended? That worked in the past. Sorry about that. As you call it, it's the Forfeit effect. I probably just forgot some very trivial thing. Team. Let me quickly check if we can fix that in the time available. Injector. So let's see. My small cheat sheet. So which one is this normal one? But these are the more. Okay, now that's as I always do it. Remote thread. This should not be necessary. Should not be necessary. We should only need this injection. Write process memory. Address for DLL path. Size of DLL path. That's all fine. I mean, if we can of course add some weight here, but that's obviously not what we would want to. Yeah, so if we add a sleep, then we nicely end up in the DLL before we end up in the other code. So with the sleep, no, that's apparently it's random. Yeah, it's too short. Let's make a whole second. A breakpoint there, and a breakpoint here. Create remote thread, then end up in a breakpoint in the loader. That's still okay. We cannot put a break on this. That's also a problem. Apparently, this break instruction gets optimized away, so that contributed to our issue. So create remote thread. Then we have a debugger breakpoint, and then we are here in the DLL. I will have to debug why resuming only the one thread doesn't work. Why I need to resume the whole thing. I will check that later. But now, since we are running out of time, let's quickly try to do something here inside our function, our DLL. So let's create a new function. Void. So as said, the process attach event should be only called once, and then we can go to our hook target. So to our hook test. Where was it? This one. And first we will want to be just very quick about everything, and just copy the code. Mostly all of it. Suck. Then we take this code. I think Windows was included already, but it's in the precompiled header. what do we have in the precompiled header? Here framework, and in framework we have Windows. Yes, so this is fine. Okay, so we have here our code in the DLL, which we can get into execution. So first of all, what we would want to do is we want in our hook target to no longer ask this question. So we can copy the string, and here we will check. So if secmp lp caption comma, do you want the program to fail? So the compare function returns 0 on match and plus or minus 1 depending which string is considered larger than the other. Right, so if we see this caption, we don't want to show a message, we just want to return what was it, id no. We want to say no because we don't want it to fail. So the first instrumentation of our message box function will just take press for us in a way on the no button, or rather not even press on the button, but make the code which called it think that we have pressed no. And then let's add some other use case. So if the program says, where was it here? The program says that it's failed, because it might claim that, we'll change that to text to sorry, we want the text, not the caption. Caption is the title. We'll change text to L. This program works great. This program works great. Or maybe like this. Yeah. This program works great. And we also want to change the message box type to what was it? mb. Okay, this stays as it is, but we want to add mb icon success. Is there a success? There was a success. This one is stop icon asterisk exclamation head information. Let's go with information. So the first message box will be suppressed, and the second message box will be altered. Let's run it. What is it complaining about? Yes, those need to be specified with an underscore because of new language conversions, as it tells you here in the error box. Okay, we don't need the breakpoint. We end up. So when we attach early enough to a process, we will always end up in a debugger internal breakpoint. So let's run it. This program works great, and that's it. It doesn't show the first message box, and it alters the second one. And of course, this strategy can be used to any function, as long as you can find the function which you want to manipulate. And of course, if you would want to change the work of some operating system functions, then this would be then you have a full documentation of most of them from Microsoft, at least of the documented ones. So like the user32 and GDR32 and many other DLLs which are supposed to be used by the user are very well documented. Some other DLLs like the NTDLL or other internal ones are not, but there are debug symbols available for them, so it is easy enough to find out what they are doing. So now what I would like to do is to find out why we could not successfully resume our remotely created thread. That is somewhat unexpected. That should have worked, and I remember before it worked always very nicely, so there must be some small stupid mistake. But one more thing which we could do is we can use a actual hooking library to do the same thing which we just did. And the advantage of that will be that doing so will give us the ability to hook pretty much any function as long as we know the function prototype, so that we can call its detour. So I have already got the right library here, minhook. let's move it into our project, and I already compiled it as well, so we'll just get the path Win64 release. No, so wait, well, that's just the temporary files. Yes, the right ones are at lib. Release this one. That doesn't look like it's new enough. Maybe I built the wrong one. Let's just quickly open it and rebuild it. Mm. Hmm? I opened the wrong file, sorry. I opened Funkhook. I wanted to open it's inside here. Okay, so I built the debug. I want to build the... Actually, why not? Let's use the debug version. That should be fine. As well, lib debug. Yeah. We need the path to the debug lib. Go to a DLL. We will need to tell the compiler to include that, so hash. We could add the library, of course, in the Visual Studio properties, but I think this will be more convenient. We need to go once or twice up. So we are here, we are there. Once, okay, only once. Oops, it was one too much. Min hook lib32. Right, and then we of course also want to include the right header, but the header is somewhere else. It's at source. Actually, does this work? Yes, it worked for a second. Include min hook. Perfect. So we have the header. We are using this pragma comment to tell the compiler, to tell the linker to include this library. And now we can, here, instead of using this hook function, this manual hook function, which we have manually botched together, we can comment this out, move this there, maybe make this like this, indent those so that it looks nicely, okay? And then we can use the min hook library. So the library first it needs to be initialized. We could of course check for an error, but we are lazy, so no. Create hook API. That takes a module L 32. That was get message box v. Sorry, just message box v. Comma. Then we want a detour function that was called my message box v. And the thing will return us here the trampoline function. So this one. But that will not compile, we need the right type. This one something like this. And we need to make a reference on that. Okay, and the way the library works is it will just prepare the hook, but to actually activate the hook we need to use mh enable hook. And then we need to tell it what do we need to tell it? Target, but the target we did not have the target address. Let's quickly see. This takes the module, but we can use another one. We can use the one without API. It's easier. So let's go now. That here we will need one small thing from our before function. Yeah, that is nicer. Do we need anything else? Nope, that's already it. And the create hook function will intelligently create and programmatically, most important, a trampoline for us. So let's run and see if it as well successfully. Do I need to use double quotation marks for that? Probably. Sorry, double escape characters for that. Try again. Yep. This program works great and it is hacked. Very nice. So as you see, the mini hook library works quite nicely and you can find it on GitHub. Mini hook, this one. And it's really really useful. So it's a bit simple in the way how it creates the detour functions. So it will not necessarily work for every single function you could ever encounter somewhere, because it uses a rather manual approach of doing it. But it should be at least compatible with most Windows API functions. So the way it was created, some guy just looked through all the different API functions and how they look at the beginning, and then created manually code that can create dynamic detours for those special cases. It's not perfectly generalized, but it is generalized enough. So if we look here in the trampoline C implementation, so that's the function that creates a trampoline for us. It will loop through the code and then always check which opcode it finds right now, and depending which opcode it finds, it will either copy it or it will change the offset when needed. And it only supports, as you see, a certain subset of opcodes. It does not support all the different x86 opcodes that could ever be encountered. So it's not a universal library, but it's still a very good and a very minimalistic library. And if you would want to use something much more sophisticated, you can use GitHub the detours library, which is provided by Microsoft, and since the last version, in version 4, it's open source and provided under the MIT license. So you can use it in all projects you might ever want to use it. And it's first of all, it's really good, really advanced. It supports not just x86 and x64, but it also supports ARM64 and I think even Itanium, even though nowadays Itanium is rather obsolete. And I think from the libraries which are really good, this is the only one that supports ARM, as far as I know. There might be some proprietary ones you need to pay for to use, which might also do it, but I don't really see a reason in paying for a library when you can just use an open source one, and especially if it's provided by Microsoft, you can be reasonably sure that the code quality will be at least okay. And since we are running out of time, a question to you all: are there any questions? No questions? Okay, so I will upload the exceptions and the Funchook test projects to Moodle, as well as the recording from today's lecture. I will try to find out why this resuming didn't work as expected, and if you are for the next lecture, if you are interested in those things, there are two options for the next lecture. Option 1 is we just start C++, and that's it. And however, if you are interested in those manual assembly writing thingy sort of things, then what we could do is we could write a more sophisticated DLL injector code, one which would not use a create remote thread, but one which would actually write some program code manually into the address space of the target process and then detour the main thread instead, or one of the functions that will be invoked during process startup. So that's definitely a bit more sophisticated, but it's much more flexible than using this remote thread creation method. So it would be good if you can think about what you prefer until next week, and let me know when we start next week whether you want to start with C++ or whether you want to start with continue with function hooking and these low-level things. Okay, so if there are no more questions, then that's that. Have a nice weekend, and bye bye.